Hello there and welcome back to this video series on control systems. Over the past few videos we have been looking at time series analysis and in particular about Weibo stability of control systems, that is bounded input, bounded output stability. We have seen that route criterion can be used to check the Weibo stability of a system. We have also seen that route criterion can be used to find the range of values of a particular parameter to ensure stability. We'll continue along the lines and follow into root locus method due to events. But before that, I think it is good if we know what we are talking about in terms of complex numbers. That is what exactly we are doing in this video. After watching this video, perhaps you'll be able to find magnitude of a complex number and know how to represent a complex number in polar form as a point, as a vector, and perhaps add, subtract, multiply, divide complex numbers. With that, let us go into the video itself. By a complex number S, we mean a number of the form S is equal to sigma plus j omega. This sigma and omega are real numbers called real part and imaginary part, and j is square root of minus 1. A complex number can also be shown in a graphical form either as a point or as a position vector. Let us see how we do that. The plane on which we draw or represent complex numbers is called S-plane. It is just a graph sheet which is titled S-plane. This has a real axis which we call sigma axis and an imaginary axis called omega axis. Sometimes we may also call it j omega axis. If you locate a point on this graph sheet whose real coordinate is sigma 1, that is, if you drop a perpendicular, this length will be sigma 1, and has a imaginary coordinate omega, sigma 1 plus j omega 1. We can represent this also as a vector going from origin to the point. Okay? The length of this vector r1 is also called the magnitude of the complex number, and along with this r1 you have an angle that it makes with the real axis, and our convention is anti-clockwise angles are measured positive, that is, this theta 1 is positive. If you consider another vector, another complex number, let us say minus sigma 2 plus j omega 2, this is negative because it is in the second quadrant. Its length is r2 and the angle is theta 2. This angle measured in counterclockwise direction is positive. Similarly, if you consider a third point as shown here, a complex number, both the real part and imaginary part are negative. The length is r3 and this whole angle, this angle is theta 3. You can see that theta 1 is less than 90 degrees, theta 2 is less than 180 degrees, theta 3 is less than 270 degrees, and you have a third complex number, the angle theta 4 is less than 360 degrees. We can also specify angles in clockwise direction as shown over here. If this is the vector with length r1, this angle is minus alpha 1, where alpha 1 is a positive quantity. Because it is measured clockwise, we say it is negative. Okay. Similarly, if you have another vector s2, which is a complex number represented by minus sigma 2 plus j omega 2, its angle is minus alpha 2, where alpha 2 is positive. So clockwise angles are negative. Obviously, we can see alpha 1, which is the angle measured in clockwise direction. Theta 1 is the angle measured in counterclockwise direction. They sum up to 360 degrees. There is a polar notation, that is notation where we represent a vector by its length and its angle with positive real axis. Let us say these are two complex numbers, sigma 1 plus j omega 1. Okay, you can represent it by its length and the angle it makes with the positive real axis. So r1 at an angle, this symbol is a symbol for at an angle. Okay, r1 at an angle of theta 1 is complex number sigma 1 plus j omega 1. Similarly, r2 at an angle theta 2, or r1 at an angle minus alpha 1. Minus alpha 1 is all this angle. This whole angle is minus alpha 1. In this context, we call this r1 as the absolute value of the complex number, or the length of s1, or magnitude of s1. We simply represent it by r1. Similarly, for another complex number, r2 theta 2 is the polar notation, r2 at an angle theta 2. In this context, if you are given a complex number, you can find its magnitude or length or absolute value by squaring the real part and imaginary part, summing them and putting them under square root as given over here. We have seen how to compute the magnitude. It's a good idea to see a little bit about the angle also. That's what exactly we'll do here. If the angle, if the point lies in the first quadrant, this is what exactly we'll do. From the point, drop a perpendicular onto the real axis, onto the imaginary axis. Let this OB, the coordinate, be sigma 1. Let this OC be omega 1. Then you say theta 1 is tan inverse omega 1 over sigma 1. Similarly, if you have another complex number in the second quadrant with length r1 and angle theta 1, or angle theta 2, r2 and theta 2. Theta 2 is this big angle, the angle from here to here. This angle theta 2 we compute as the total angle in the line EB. That angle is 180 degrees. From that you subtract this little angle psi. 180 minus psi is theta 2. And the psi is tan inverse omega 2 over sigma 2. Omega 2 is the length OE, and omega 2 is length OF, and sigma 2 is length OE. Find what is this psi. 180 minus psi is your angle theta 2. You need to remember this very clearly. Okay. Instead of blindly saying tan inverse minus omega 2 or sigma 2, it's a good idea to compute this angle and subtract it from 180. Similarly, if the angle is in third quadrant, we write it as 180 degrees plus beta, where beta is tan inverse this quantity. When it is in fourth quadrant, you compute this little angle and say that this angle is gamma. Gamma is tan inverse omega 4 by sigma 4. Next, we'll see how to subtract and add complex numbers in algebraic form, that is the form given here, real part plus j times omega part. You can simply sum up the real part, sum up the imaginary parts, but it's a good idea to see how we do it in geometrically. Let's say this is one complex number, sigma 1 plus j omega 1, represented as a vector, and let us say there is another vector representing this complex number. Now, if you want to subtract this z5 from s1, you draw a vector from the tip here to the tip here as shown here. So this vector is the result of subtraction, s1 minus z5. Just remember that s1 minus z5 is a vector going from z5 to s1. Its angle is minus alpha 5 with the real axis. In this context, it would be good to remember that the length of this vector AB equal to magnitude of S1 minus magnitude of Z phi. If you do that, it would be a total blunder. Having seen subtraction, let us also see how we add two vectors. Let us say this is one complex number represented as a vector, and this is another complex number represented as a vector. To sum them up, you will build a parallelogram on these two. That is one side, this is another side. You can see that this is a nice little parallelogram. This side parallel to this side parallel to this, and the sum of these two complex numbers is a third vector whose angle is beta and whose length is equal to OB. Of course, it is easiest to compute the sum of these by just summing the real numbers and real parts and imaginary parts, but it's a good idea to know how to do that graphically. We have seen that there is one polar form, R1 at an angle theta 1. It can also be written as R1 e to the power of j theta 1 and expand it as R1 multiplied by cos theta 1 plus j sine theta 1. If you represent two complex numbers in this way, their product can be obtained simply by multiplying the magnitudes and adding the angles. Similarly, their ratio can be found by dividing the magnitudes and subtracting the angles. It's a very good idea to remember this. We may be using this a couple of times. With that, we will summarize what we have seen. A complex number may be represented as a point in a plane. It may be represented as a vector. It may be represented in polar form, R1 at an angle theta 1 and so on. Or you may write it as R1 e to the power of j theta 1. Okay. Angle is positive when measured counterclockwise and negative when measured clockwise, and addition and subtraction of position vectors may be performed by using parallelogram law for vectors. I think that's all we have for now. Have a great day.